And now I would like to share the room to start the session of today's. And today's session or today's activities are divided in 4 moments. The first half of the day has presentations by Suzanne van Eekelen, by Amin Askarinejad, and Stefano Muraro. And then in the afternoon, we will have some presentations by Juan Wang, Dr. Juan Wang. I will be presenting a bit of that. And we have our keynote presentation by Professor Brown. So the first presenter is Suzanne. Suzanne did her PhD in TU Delft and is one of those very successful PhDs that is directly translated into a guideline. So it has a direct impact into how people build things and how the knowledge gained from research is useful for that. And she will be sharing with you some of the concepts of wetting and drying cycles in this and disappearing soils. That is a very appealing type. So thank you, Suzanne. The floor is yours.
Thank you. Hello, good morning. I'm indeed Suzanne van Eekelen, working at Deltaris in Delft. That's not a university, it's a knowledge institute. I've been working there for more than 30 years. I did my PhD when I was ancient. I was nearly 50 when I defended my PhD, and that was on piled embankments, geosynthetic reinforced piled embankments. I'm an expert in geosynthetics, but I'm part-time an advisor, so I'm a consultant, geotechnical engineering, and that deals with a lot of issues in geotechnical engineering, like, for example, retaining walls, road construction, railway construction. And the other part of my work is research. I'm the facility manager of the facilities of Deltaris. We have a geotechnical centrifuge and a geo model hall for 1G testing. And today I will tell you about 2 subjects. The first one is wetting drying cycles. That means making things wet, making things dry, and what would we like to measure in those experiments. And then the second subject is disappearing soils. That means when there is some volume loss in the soil, for whatever reason, how do we model that in an experiment? Well, starting with wetting drying cycles. An increasing problem, of course. The climate change gives that we have longer periods of drought followed by heavier rains. Of course, one of the results of that drought is those cracks in dikes, and that those are followed by wet periods. And as you can understand, water infiltrates in the dike more easily when these cracks occur. But that's not the only thing that happens. Here we see the result of a drought period in the Netherlands. There was a dike that was that became very, very light, and it just floated away during a hot season. And that was exactly at the moment that there was an international conference on geoengineering in Poland. So all the Dutch experts were not in the Netherlands when this happened. But what happens too, apart from those cracks and the easy infiltration, is that the soil behavior really changes when you have wet, dry cycles. There is some research done here in a container of 1 meter diameter filled with sand, a plastic clay soil, and they fully saturated it. And then they started to let it dry. So it dried slowly, like this. And during this drying process, they did little CPTs in it, a lot of them. And so that they in each CPT, they also measured the water content by measuring the total weight of the system. And then they made it wet again and took a lot of days to make it wet again. And then they did another drying period. And then they did that again. So they did 3 periods of drying and doing a lot of CPTs during this drying. And this is the result. Here on the horizontal axis, we see the average water content in the sample. And on the vertical axis, we see the cone penetration resistance they measured. And this was during the first drying period. And then they made it wet again, and then they did it again. And what do we measure? With the same content of water, they consistently measured lower cone penetration resistance. And this is the result in the third cycle. So the difference is much smaller. But this shows that the behavior of soil really changes due to that wetting drying. Another interesting research is this. They just made a mixture of some slurry of clayey soil, made it wet, dried it, made it wet, dried it, made it wet, dried it, and made it wet, dried it. And you see cracks occur and they change. After the first drought period, we have really different crack and less cracks than in the later periods. So that's another observation. So we have seen that wetting drying cycles can change the behavior of a soil body, like a dike that floats away, or a dike that just collapses, like shown here. Then expansive soils can give excessive deformations, and water transfer canals can give more seepage, so they can leak. So water comes out of the canal more easily because of wetting drying periods. So now we are here to talk about physical modeling, and we are going to look at this experiment, a wetting drying cycle on a slope. So first option is that we look at the wetting of the dike from beneath, like this, so the water table increases and decreases. A second option is that we have water from above, rain and sun, and rain and sun. So rain and evaporation, rain and evaporation. We would like to be able to do both. Hello, Amin. I see Amin, and he knows everything about the rain, the modeling the rain in experiments. First, we need to make a model. And I think you have already talked about it, at least during the nice excursion we had yesterday. We were told about making models, but we will go through that again. First sand, then clay, then peat, and then how to make an heterogeneous model. So sand, air pluviation, we saw it yesterday. And what we want is we want to know the relative density of the model. And that can be adjusted by the drop height, the hopper velocity, and the opening in the box. So you have an influence on the relative density due to these features. But then if you want to have a dry model, then that's it. If you want to have a saturated model, you talked about that too. And you did that very well. So maybe. There are several options. If you have used a dry model and you want to have it wet, then you can just saturate it, and then you will reach a water content around 90%, which cannot be enough. If you use You told that very nicely yesterday, vacuum and CO2, and you can flow that through the sand and you remove the air and then you will have a saturation of 95%. Eva says I say it well. And then in flight, you can even get a higher water content. Making a slope, Luc told me last year that in France they can make perfect slopes from dry sand and then saturate it. We usually do it in a different way. I still would like to see how they do that. But we usually, at Deltares, we usually start with water and then we flow the sand into the water. And that cannot be done with a rainer because then you will not have a very dense model. So we rain it in ourselves and we stamp it during the pluviation. So now in this way we can have a 100% saturated model, and it's also easy to install saturated pore water transducers. And we can use suction, and I will show that. So if we use suction, we can easily cut a slope into the model. But the drawback is, the density control is less easy. So what we do, we pluviate dry sand in the water, and if the model needs to be relatively loose, we just pluviate it and then we poop, 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 poop it, or we tilt it a little bit and then we drop it 1 centimeter, and then we have a uniform loose sample. If we want to have a dense sample, we pluviate it in and then we stamp. And that works really well. We have a lot of experience. We can produce homogeneous, repeatable densities. Sometimes we need a viscous fluid instead of water, because in the centrifuge, the water flows really quickly, and sometimes that's not what you want. And then we use viscous fluid. That means more work. So we only do that if that is necessary, and we replace the water with the viscous fluid if necessary. We can lower the water table, so then we create a suction in the sand model, and then it is easy to trim it into a certain shape. So this is how we do it, but there are many possibilities to model, to make such sand models. A summary, I first told you about making a dry model using a sand hopper, and then water saturation. And then I told you how to rain sand into water. But alternatives exist. I will show you one more example more. We can just rotate the box. So we want a model like this, but we close it at the top side, and we remove the wall at the side, and then we turn it, and then we can fill it like this. We can replace the fluid if we want so. And then we seal the side, we rotate the box, and we open the top. And then we can lift the mold. So, but more methods exist. Going to peat. Peat is difficult in a centrifuge. I'm not sure, was it discussed already? Peat in a centrifuge? No, there are fibers in peat. There are different types of peat, of course, but in many peat types you have clearly visible fibers. And then if you spin that in the centrifuge is 100 G, then such a small fiber turns into a tree. So the behavior of such peat in a centrifuge is difficult. If you really want to use peat in a centrifuge, and we actually do that, we try to use deteriorated peat, so old peat with less fibers or small fibers. And we also can make artificial peat with small fibers, but it is difficult. And what we do, we can make large samples from peat. We developed a sampler that's able to make samples like this, as shown here. And from this, we can cut peat samples. And this works. And for GeoLab last year, we also we did centrifuge test for one of the transnational access projects. And that was for Norwegian and Irish researchers. And they brought their own peat in the car, in the boat, during a storm. And the sample survived and was fine. And you see here the lowest picture, that Norwegian peat sample with some yellow color powder at the surface. That is for you doing PIV. So be aware of scaling effects in peat testing in the centrifuge. Use decomposed peat as much as possible. And very important, peat has chemical processes. We have oxidation, it just disappears when it is in contact with oxygen. You cannot model that in a centrifuge. The centrifuge is meant to do experiments where the stress is the major cause of things that happen. So it's stress-driven research. You cannot do chemical things in it. And aging like deterioration or decomposing is not to be modeled in a centrifuge. But still, it can be interesting. This is that GeoLab transnational access project. They installed a small embankment on that natural peat from Norway, and this embankment is lightweight. You can see that it's different materials. It's partly sawdust, so that it is lightweight. And the major purpose of this research is that in Norway, it is forbidden to excavate peat because that gives a carbon footprint, too large for carbon footprint. So they want to keep it where it is and to construct across it. And they already did. They constructed an embankment on natural peat in the 60s, and they have measurements of that. And with these tests, they wanted to simulate those field roads that already exist and to learn from it. Then clay. We use in the centrifuge two types of clay, roughly, natural clay and not natural clay. So this is this picture shows an artificial clay, kaolin clay mixture. First, we have a slurry, we mix it under vacuum, and then we need to consolidate the sample. And there are two ways to do that. One can be in flight, in the centrifuge. That requires sometimes to spin days and nights. Sometimes it's sufficient to do it when you have thin layer. You can do it in for example, 10 hours, but or 20 hours. And sometimes you need to do it day and night. And not all centrifuges can be left alone during the night. We recently opened our new centrifuge and we are able to leave it during the nights. So we can spin over 3 nights, for example. How long does it take, this consolidation? In comparison to the real situation, I think it was told yesterday that that's the square of n. So if you use 10G, then it will go 100 times as quick as the prototype situation. So that's the reason that we sometimes call a centrifuge a time machine, because we can do the consolidation quicker. The result is a normal consolidated clay profile, and it is of course difficult to put sensors in it. And I think this is the main reason that we usually consolidate 1G. Or most of the consolidation is most of the consolidation is done at 1G, as shown here with a press. Then we can make several layers with a different consolidation pressure. We can make a choice for the consolidation stress, and it is easier to put instrumentation between the layers. Here we see clay bread cut from such a sample that was pressed. It's removed and installed in the model. And there it is in our strong box. We are currently working on an uplift problem. That means we have a layer of sand and above that a layer of clay. And this clay was made of natural clay. It was taken from the middle of the Netherlands, where we have human-made area in the Netherlands. There we take clay, and we did it already more than 20 years ago from that same location. And then we start mixing it in this silo. We mix it. And then we put it into the mold just by hand. So you see black natural clay. And then it's consolidated in the press under 1G. And this is a very huge deposit of the same type of clay. And to have it so reproducible, we mix it and we handle it like this. And there is the clay bread. This is not always successful. This is sometimes a cause of stress, because sometimes something happens. For example, one of the last time there was a crack in the clay somehow. So something happened, and then they have to start again. And that means that all schedules must change, because such a thing takes a month or something like that. So having the clay bread ready in time is a cause of stress. Then what about 3D printing of soil? A lot of developments were done in the recent years. Of course, 3D printing is already a while, but 3D printing of soil is another issue. So there was a proof of concept with fine-grained materials, but I would like specifically to show you two other things. And that's a research on the influence of the shape of the grains. If you really want to research this systematically, then it is nice to be able to print the grains 3D. And here they produced some shapes of grains that were based on natural grains. And then they put one shape, a lot of grains of one shape, into a triaxial test. And then they did triaxial tests. And that is a very nice result, I think. Then you can see, for example, that in the top graph, the lowest picture, that's the circular grains. So we see in the triaxial test that we have less strength for the purely circular grains. That's as we had expected, isn't it? And then what they concluded, one of the conclusions was that longer grains give relatively a lot of stress, more than the angular grains. So the angularity is of less importance than the width-length ratio of the grain. Another research is the permeability. How is the permeability of a grain affected by the shape of the, so how's the permeability of the soil affected by the shape of the grain? So then basically they were able to do the same research with permeability tests. And then clay. Clay can be very heterogeneous. And usually we have, in the way we prepare the samples, we have a homogeneous sample or maybe a normal consolidated sample when we do it in the centrifuge. But what if it must be heterogeneous? So quite a lot of research was done. On the left-hand side, we see a 2D sample done by a Columbia professor, Lina Garzon. Do you know her? Yep. So this was already a while ago, and she used group theory to determine how the heterogeneity must be done, and then they made this sample, which was quite successful. They tested it, and then later on, other researchers made a three-dimensional sample, more or less the same way. They used mixtures of bentonite and kaolin, and printed it with these different types of clay. They made a color to be able to see what clay is where, but the behavior is the liquid limit was different. So the water content was different, and the mixture of the bentonite and the kaolin was different, resulting in different behavior. And they actually tested this sample and found really different results, of course, than when the model had been heterogeneous. Here on the left-hand side, we see one of the layers directly after printing, and on the right-hand side, you see the theoretical numerically determined distribution that they wanted to produce. And well, nice result, I think. It's not the case that we have done so already. Well, so far making the models. Then we will continue on how do we make it wet and how do we make it dry, the model. So how can we activate the wetting drying cycle? Well, wetting, we might be interested to do it from above, like rain or injection, or we might be interested in doing it from below, and we will see both. Or from the sides. And then drying, we can just wait, natural evaporation. In the centrifuge, that goes quickly. Or we can inject dry air, or we can use heat. Well, this is, I will show you some examples of how people did it, and some of them are of us, most are not. Usually, a climate or an atmospheric chamber is used. I think in France they have a very nice one in the group of Luc. We don't. And there in such a chamber, just a box in which you install the model, you can fully control the humidity, the temperature, and the air. Here you see a window, a camera, as a rainwater inlet, rain nozzles to have very fine drops. Because if you do just rain in a centrifuge and you have a real raindrop like we have it outside and it falls on the clay, then it is like a bomb. So that's not usable. So it must be very, very fine, misty, like small rain nozzles. And dry air inlet. These researchers did tested 40G, and they did 3 wetting drying cycles of 24 hours each. First, they did a misting nozzle, so very small water droplets on micron scale. And then they injected dry air and let it out at its heights. And it was like this. So they had a silty clay, and they increased the water level just like this, horizontal water level. Then they waited for 30 minutes. And then they dropped the water via the inlet and outlet. And they used heating tubes for 15 minutes. to dry the surface. Then they increased the water level again, waited 15 minutes, and then they decreased the water level again, and it filled before they were able to use the heating system again. This is nice, isn't it? The first decrease of water level, nothing happens. Second decrease of water level, it fills. This is another research looking very much like the one that we are doing currently. Here we have a slope again, a soil body again, and on the left-hand side, there is some nailing in the slope. It's relatively steep, we see. On the left-hand side, we see a drainage board. That's just a stiff board with some holes in it, so that water can flow through, inlet holes. And on the downstream side, on the right-hand side, we have another board, also with an outlet hole in it. And they control the water level at each side. An upstream reservoir and outlet hole. And one of our centrifuge GeoLab transnational access projects we are going to do in the coming months will use more or less the same system. The nice thing is that you can flow the water in from the full side. And we course block. So the water level was increased like this on the left-hand side, not on the right-hand side, and then you will have a flow in it. So water level was kept high for a while, and that's it. I will tell you now about centrifuge tests we are currently doing in cooperation with TU Delft, where the experiments were done without the soil body, I think. Isn't that? Are you involved? Yep. So it's uplift research. That means we have a high water pressure in the sand layer underneath. And then on top of that is a layer a layer of soil that is relatively leak-proof. For example, clay or peat. I did such centrifuge test myself 20 years ago. And then we used organic soil that was very lightweight. And then if the water in the river increases, the water pressure in the low sand layer increases too. And then the soft soil on top of it can uplift, can be pressed up. So that we call this mechanism uplift, as shown in this picture. And then cracks can occur. You can have horizontal pressure on that soft layer, and then a failure can occur. We actually had a failure in the Netherlands of a dike in 1984 that was purely due to this mechanism. So the water in the river was relatively high. The dike itself was fine, but the soil behind the dike was not fine because it was pressed up. And we use our strongbox, which has nearly 90 centimeters long. And this is the model. We have sand and soil layer with low permeability and a dike. Oops, yeah, well, this is not for now. And here on the left-hand side, we see the reservoir number 2, where we control the level of water at the left-hand side in the box. And it is controlled by the plunger, yeah, on the left-hand side. There we increase the height of the tube, and that is connected to the reservoir. So if we pull the plunger up, the water level on the left-hand side of the box increases. And when we do it down, the water level there decreases. So it's a rather complicated test setup, and that caused a lot of delay too, because it's a lot to put in the basket in a centrifuge. It does not fit, it is complicated, and that gives delays. But I'm happy to tell you that we did a second test this week. in and out. So this is another research, a very nice research in my feeling. It's a railway simulation system where they can simulate the load of a train, of a high-speed line, very well. It's in China, and the same test setup is available in Madrid, CEDEX. They were first, and they can really induce the load that a passing train gives at any speed. And the nice thing is that there's the rotation of the principal stresses that's typical for a passing vehicle, that is modeled really well in this situation. In this case, they constructed a piled embankment underneath this railway loading system, and they increased water level during the testing and decreased it and increased it and decreased it. It's very nice research where they measured a lot and learned a lot. And they just inserted the water via tubes next to the rail and let it flow into the soil. And they measured the saturation with measuring devices during the test. And then we did it a little bit simpler. We just put our piled embankment test setup in bath together with the duck. And then we increased the water level and decreased the water level and increased it again. And through openings in the test box, the water was flowing into the sample. So far, how we do the water, the wetting and the drying. So we have talked about the modeling of how to model the soil models and how to activate the wetting drying cycles. And now what would we like to measure and where during those experiments and after? Well, first of all, always in each physical testing, know your model. So we need the soil properties, and in GeoLab we have nearly available an overview of the soil types we frequently use. So each facility has his or her own sands or clay types they use frequently, and we have now made available a full list of those material properties. And these are specifically made to make it possible to do numerical calculations on them. So within GeoLab, a lot of available for this. And of course, the geometry. It's amazing how often afterwards we forgot to measure the exact location of this single transducer. So when you do the experiments, always write down everything and always make 4 times more photos than you think you need, or 10 times more. From different perspectives, from details, from overview, from everything. Then know the testing procedure. So the rain intensity, the amount of input and output water, air pressure, pressure on the rail control system, the water level, the saturation, the relative humidity and the temperature. And we will look into some of these, the deformations, the stresses in the water table. Yesterday, I think you had a great lecture of Sam Stanier, who is an expert in that PIV. I attended his lecture last year, and I was very excited about his clear presentation. So I don't need to tell you about this. It's nice to have high resolution cameras, and he must have told you that the size of the cranes and the resolution of the camera has something to do with each other. Then this is one of my field studies. This is a piled embankment, and we will come to that later in the second subject too. Here we have settlement tubes installed and connected to geosynthetic. And what we then do when you have such tubes, they are also installed in embankments in general. We put a device into that tube now and then we pull it back. And usually each 50 centimeters you stop. And what we do is a water pressure liquid leveling system, this system. So a water pressure transducer in a tube with fluid connected to some bucket with water. And from this you can measure the vertical position of your transducer at a certain point. And this is a very usable system. We use this in experiments a lot too, with just single point measurements, but they are very reliable and consistent. There's just a picture of a linear variable differential transformer that to use to measure the deformation of some surface. New since 10 years, maybe, optic fibers. You have seen about this already or not, about optic fibers. I installed optic fibers in a piled embankment in 2010, I think, and it is really great. When a truck passes, you can really see the first axle, the second axle, and the third axle. You see small strains in soil, in the piles, in the geosynthetic. It's fantastic, but also very time intensive. If you have results and it must become a graph in your thesis, there's a lot of time in between because there are always a lot of errors that you have to solve. There's distortion. It takes time. We have done measurement with this system recently, also in GeoLab project. I will show more of it later. And here, the same issue. The measurements are absolutely fantastic. We can measure X, Y, Z deformations in the full soil body. So we have at several levels, we've installed this system, and the results are fantastic. But it takes a lot of time. And then final slide on this subject, pore water pressures. Oh, this is not the final slide, more to come. Here, this is a field measurement of pore water pressures. There are two. The orange one, PPT6, pore pressure transducer 6, and PPT1. And the dotted lines show their location. So the blue one is installed on a level of -2.5 meters below the Dutch general level. And the orange one is higher, at -1.7 more or less. And what happens? We see on the vertical axis, we see the groundwater table that was measured with these pore pressure transducers. And these two transducers agree until a certain point in the beginning of June 22. What happened? What happened in June 22? That these two pore pressure transducers stopped with agreeing, with matching. Does anybody have an idea? I think you were right. Yeah, the water table crossed that pore pressure transducer number 6. And what happened? An air bubble came in front of this transducer. And so it was disturbed. So pore pressure transducer 6 had an air bubble, was not saturated anymore. And it stopped with giving reliable results. But after a while, the same happened. And that was in beginning of September of 2020. The water table crossed the pore pressure transducer again, and that was enough to push away this air bubble. And then it started working properly again. So this shows that it's very important to keep those pore pressure transducers saturated. Now there are also options to measure pore pressures with optical fibers. And Amin, who's there, did this work. He installed an optic fiber on the surface of a pile. Please correct me if I'm wrong, Amin. It was installed on the surface of a pile behind this really tiny thing with an small tiny air chamber in it and a flexible membrane on top of it. If there was some fluid pressure on this membrane, the light changed in the air bubble in that air chamber, and that gave a different signal to the optic fiber. So this way, the optic fiber is able to measure pore pressures. And this is not so sensitive for saturation. So this might be a solution in the future for measuring pore pressure at locations where you cannot guarantee the saturation. So this is a very interesting development, I think. So we have talked about pore pressure transducers. Then there is a thing like suction forces. If you don't have a fully saturated sample, you will have suction forces. I'm not sure the link works in the PDF I sent you. This is a small lab tensiometer, and that can measure the dielectric constant and then a lot of difficult things. And the final property that you can measure with this thing is the volume water content, and that gives the suction forces. And then, of course, after finishing the test, you can take samples and measure the water content. It is simple, but it is necessary to do it if necessary. Think about it. Then there are more developments, of course, like a special digital camera. And that is somebody here. It's you, isn't it? Yeah. Who's going to try this in the GeoLab transnational access tests that we will do in the next months, using a short wave infrared images to measure the degree of saturation. I think you have tested this already. Just with sand, okay. Well, it's an interesting development, I think. That it may be difficult to combine this with the plexiglass wall of an average strongbox, but it's a very interesting development, I think. So far, the wetting and drying, I suggest that we take 5 minutes break to have a cup of coffee and then come back 5 to 10 minutes, and then we will continue with the next subject, disappearing soils. Yeah, this is really a new area of research that you might have recently done. Two projects. We will start again in 1 minute. Please proceed to your chair. Disappearing soils. I will talk about disappearing soils, and we will look to why do they disappear. But first I will introduce a piled embankment to you, which consists of a field of piles, sometimes depending on the country, with a pile cap on top. And then comes a reinforcement, usually a geosynthetic, usually first across and then along. And on top of this comes an embankment. And this embankment consists of sand or broken rock or a broken construction material. And sometimes in some tropical countries, tropical soil, that's right. And on top of this comes a road or a railway or any pavement. And within such an embankment, arching occurs, soil arching occurs. And that means that the load tends to be transferred towards the stiffer elements, which are the piles. Well, underneath this reinforcement, the soil tends to disappear. Not always like this. Here we see soil that is really washed away by a flood, and still the piled embankment, it worked still. You see the geosynthetic hanging, sagging between the piles. This was in Malaysia, and there was flooding, and that the soil was washed away. But even if that's not the case, the soil disappears in many cases. And that is because there is underneath this reinforcement, there is often a working platform consisting of a layer of sand to make it possible to install the piles. And that gives a consolidation of the soft soil underneath. And the result is in many cases like this, a gap underneath the reinforcement. And if we would like to do research on this subject, then we need to be able to model that the soil disappears. And many subjects, this is an issue. For example, you can have a consolidation of a layer, like in this case, but you also can have erosion, so some water leakage or some water flow through sand, and when the sand can go anywhere, then it will go there, and that leaves a gap, for example. Or you can have soil that dissolves, like karst stone that just dissolves in water. Or you can have soil that collapses because there are cavities underneath. So there are many causes why soil disappear. And we are talking about that, how to activate disappearing soil in a physical experiment. And I will lead you through doing that on the case of piled embankment. And in this piled embankment, in the research for this piled embankment, we were interested in developing a calculation model to predict this, the strain in a reinforcement. And here you see this strain. The reinforcement sags in between the piles because we have a cavity or a gap underneath, or just some consolidation underneath. And then that causes that the reinforcement gets longer. So we have strain in it, and we want to be able to calculate this strain on the basis of observations in experiments. And now, in the experiments, how do we activate this disappearing soil due to subsoil settlement or consolidation or erosion or dissolution or whatever? Well, one thing that was done in practice, in physical modeling practice a lot, is a trapdoor. So here we see that we have a plate that is segmented underneath the model, and part of that plate just goes down slowly. That is a trapdoor. And here we see some experiments with trapdoors. And these experiments are 2D. So we have a plate in the 2D model, and it just lowers slowly. There are hundreds of publications about this system. A very nice test setup of Luc Torel in France, and a moving tray for the centrifuge. A lot of piles go through this plate, and the plate can be lowered slowly. So that models the disappearing soil. Many publications, a lot of research, very nice. This case I do not recommend. Here a lot of piles were installed, and then reinforcement, and then an embankment, and then somebody went underneath and dug the soil away. I do not recommend this. This was done in Singapore, I think. But it resulted, maybe it was Malaysia. It resulted in a nice PhD thesis of Le Hello done in Grenoble, and yeah, it worked, of course. Here the soft soil is modeled with peat, done in the University of Kassel in Germany. Several Saaske and Heitz did their PhDs on this subject. They used peat, which is compressible, so no gap occurring, but consolidation or settlement occurring. Then several researchers used some foam. Sometimes, specifically in a centrifuge, they used EPS, but other types of foam were used too. And then both foam blocks and foam grains were used. And of course, no cap is occurring, but consolidation can be modeled more or less. So you have a settlement. This case, Chinese research. On the left-hand side, we see the test I showed you earlier with water, and the test setup where a railway, a train load is simulated very well. They used water bags in between the pile caps, and they were just emptied. The same is true on the right-hand side, also Chinese water bags, a sand embankment on top of it, and the water bags were just emptied. This looks very much like this research, which is not a piled embankment, but a pipe done in our centrifuge in Deltares. There we had a small balloon specifically fabricated for this purpose. It was filled with water. It was attached to the pipe, and then in the centrifuge, it was emptied due to the gravity force, and then a cap occurred. And this modeled the erosion cap that sometimes occurs around pipes. So here we see the pipe through the glass window, and underneath you see the balloon. This was done in Brazil, and this is EPS, and they dissolved this with orange peel juice because EPS dissolves in orange peel juice. Large-scale tests. And this is done currently in France, large-scale tests on piled embankments. And here they use the cardboard and they just make it wet. And when you make cardboard wet, it Now about our research, which was the basis of my PhD, we had a test box for 1G circumstances with 4 piles in it. And in between it, we had a soft soil, which consisted of a foam cushion that was fully saturated and wrapped so that it was leak-proof. There was a tap attached, and when we opened the tap and pushed the soil, the foam cushion, it looks like this, then it starts consolidating. So when we open the tap, and only then, and we push it, the cushion, and only then the water starts flowing out. So simulating the consolidation of soft soil exactly. And we did the first test in 2009, and the last test we did in April this year. So we are using this test setup frequently for different configurations. So this was a photo of this test setup with this foam cushion of last April, where we did GeoLab experiments. On top of this comes a layer of sand, and then comes a stiff steel frame with a geosynthetic attached. Here you see it come, and we see strain gauges attached to the geocrypt. And in a recent test, we used a steel reinforcement. We did those experiments with German and Polish partners. And then comes the rest of the box, and a fill is installed. In many cases, it was broken, crushed concrete or masonry or some recycled construction material, because that's the most common construction material in road construction in the Netherlands, because we do not have mountains or rocks. In some cases, we used sand. And then a surcharge load was applied using a water cushion. And on top of that, it was locked and closed. And then we were able to supply a surcharge load of 100 kPa. These are tests done already 10 years ago. And later, we increased the height of the test box. And the test goes like this. In steps, we increase the surcharge loads, and we let the foam cushion consolidate. And then in the final phase of the test, we suck the foam cushion vacuum so that a cap occurs and the soil has disappeared. So do it again. So first, the gravity force and the surcharge load gives the consolidation, and then we suck it vacuum and the soil disappears. This water cushion is not easy to make. We did it first ourselves. We painted a watertight, a leak-proof cover on the foam, and it worked more or less 4 times, and then it was leak. And then finally, we found a water bed manufacturer who was very enthusiastic to make such a cushion for us. And he's still working for us now and then. He's just a water bed manufacturer and sometimes making very strange cushions for us. These are the recent tests we did. And now we are, for the same GeoLab project, we are also going to do nearly full-scale tests in Germany and Darmstadt. And that's the second part of the same research for GeoLab. And here we make a combination of an elastic support that gives some elastic deflection underneath the reinforcement and the occurrence of a cap. And that works as follows. Here we have the pink layer. We have a rubber, a granular rubber that's able to give some support, but will also deflect. And below that, we have some hydraulic jackups, and we can lower it. And that works as follows. We will first install the sand layer, and then we will decrease the level of the low steel plate, the bottom steel plate, where the rubber lies on. So then you see that a cap occurs underneath reinforcement. I made this animation yesterday. So this, I've never seen this before. Here we make the combination of an elastic support in the initial situation and the occurrence of a cap later. And this is what happens in practice in many cases, because you do not lose your subsoil support immediately, but after a while, it often happens because consolidation occurs underneath section piles embankment due to the weight of the sand underneath the reinforcement, or for example, due to water level, groundwater level changes. For example, due to some construction activity close by where the water is drained out. So we have seen several possibilities to have the soil disappeared. You can use a trapdoor. You can just remove it, which I do not recommend. You can use some Peter soft soil, but then you will only have deflection, not disappearance. You can use foam or rubber. You can use water balloons or water sacks, water bags. You can dissolve, like the EPS in the orange peel juice. You can use that soaked foam cushion that is wrapped and leak-proof with a tap attached. And then the last example I showed you was a combination of rubber and a moving platform. So now, so far, how do we induce the disappearing soil? And now we will look at what we would like to measure, and then specifically in the case of a piled embankment. And for this reason, I will explain you some basics of piled embankments. How do we design the reinforcement in such a thing? Because that's less daily design for many designers. And that's done in two steps. What we want is we want to be able to calculate the strain in the reinforcement. Because if you have that and you have the stiffness, then you have the force, and then you can have decide which strength is needed. And that strain in the reinforcement is calculated in two steps. And the first step is that we divide the load into two parts. One part goes to the piles directly. And that's a relatively large part, and that's due to arching. Arching is of great importance in our geoengineering subject, because if you have some element that moves less than other elements in the soil, then the force will go there. So if you have a certain part in the soil that's compacted better than other parts, then the load will go there. If you have a sheet pile wall that is behaving stiffer at some locations than at another location, then the load will go there. And the same is true in a piled embankment. The pile moves less than the area in between, so the load goes there. That's soil arching. And we can measure this. And then in the second part, we will calculate from the other part of the load, B plus C, we will calculate the strain in the reinforcement. So the final load distribution is like this. Because in the second part, it's too far now to explain everything, but the second part of the load partly is transferred towards the piles and partly can rest on the subsoil if it is there. That is C. Now, how do we measure this load distribution? The initial load distribution can be measured with that device A on top of the pile above the reinforcement. And that's not always easy, because in a centrifuge test, you have a very thin layer of for the embankment, and a transducer has a certain thickness, so that makes it difficult to measure this. In practice, you have more space, or so that in practice we have installed it in the field and in 1G experiments a lot. Underneath the reinforcement, we measure A plus B. On top of the reinforcement, in between piles, we measure B plus C. Underneath this reinforcement, we can measure C. And this is always difficult because the load there is small and usually decreases. And decreasing load is difficult to measure. It's very important to calibrate the pressure cell for decreasing loads if you expect decreasing loads. So you always have to calibrate each instrument before installing it, and best to try a load that you expect in the experiment. And if it is decreasing, use decreasing load. Theoretically, it should give the same result, but it is not always the case. Then in the case of our experiments, we also measure the total load on the steel stiff plate underneath the soft soil. The pressure in the foam cushion, C, should be the same as the total force underneath the foam cushion. So different ways to measure the load distribution. So C is measured in 3 ways. There's a total pressure cell underneath the reinforcement, which actually seldom gives good results. We measure the pressure in the foam cushion, in the soaked foam cushion, and we measure the force underneath the steel plate under the cushion. And those 2 match very well. So here we see some of the transducers installed in our experiments. A total pressure cell on top of the piles above the reinforcement, pressure cells in between the piles. Yeah, and in the left-hand side, you do not really see a photo of the pore pressure transducer in the foam cushion. This is in the field. Here we have 85 centimeter wide pile caps and a total pressure cell of exactly the same size on top of that. That weighs 200 kilos, the pressure cell itself. They work really nice, already 12 years. So here we see some measurements in experiments. And on the horizontal axis, we see the height of the embankment. On the vertical axis, we see the total load that goes to the pile directly. And here we see some predictions. This way we can compare different models with the measurements. I'm not sure what I was going to tell you. These are German experiments, very much the same as ours. That's because they were first and we copied their experiments and changed some details. And here they measured the vertical pressure above the reinforcement if it was there. So these results are without reinforcement, but at the same position. And what we see is that the yellow, blue, and red ones give more or less the same results. And now they repeated the same experiments, but now with a reinforcement. And what do we see? A really different result. We see that the red one takes much more load than the yellow one. And why is this? This is also soil arching, because the reinforcement between 2 adjacent piles deflects less than the reinforcement in the middle between 4 piles. And if something deflects less or moves less, it attracts more loads. Of course, the piles attract most load because they move least. But the reinforcement at certain places moves less than at other places, so more load is attracted towards that area. So when we did our research, we were interested in how the load is distributed on the reinforcement. That was one of the main things we actually did, and the findings we were able to explain later. And how did we do this? How did we determine which of these will be most applicable? Well, there is a direct relationship between the shape of the deformed geosynthetic and the load that's exerted on it. And when you have a fully uniform load, then the shape of the geosynthetic will be a full parabola, like this. If you have a triangular load, then the shape will be like this. And if you have an inverse triangular load, then the shape will be like this. And we can measure this easily. We can measure the shape of the reinforcement. And so we did. We did this with the water pressure meter in the tube with liquid, so the liquid leveling system. And we also did it with measuring the geosynthetic before and after a test. And then the difference between the shape was like this. And we were able to make cross sections through these measurements. So we were able to compare these measurements with those theoretical shapes. Now the separate point measurements were like this. And here we see that all the measurements are on or outside the green line, which corresponds to the inverse triangular load distribution. We also measured with the scan transducer, we scanned this shape in one direction, and in the other direction we had this shape. So from this, we concluded that all measurements were on the green deformed line or outside. So apparently this load distribution is better than the others. And then we looked in the field. Here we have an exit of a highway, and we have those settlement tubes attached to the reinforcement. The subsoil support disappeared quickly. In this case, there was a thick peat layer and a sand layer on top of it below the reinforcement. And after using the road for, this is the same, it's another project, also settlement tubes installed coming out at the side of the road. But in the first project, we measured the shape of the reinforcement after using the road for 1.5 years. And this was the result. And we see those 3 piles, and we see the shape of the reinforcement, and the difference between the highest and the lowest point is around 14 centimeters. And from this, it is possible to calculate the distributed loads directly by taking the second derivative. And that results in this. Of course, it's not very smooth, but this is very much more like an inverse triangle than like a uniform load distribution or a triangular load distribution. So we measured the load distribution not by measuring the load, but by measuring the deformation. And so the conclusion is that what we saw already that most load goes to the area between the piles and not in between, and that the load distribution on those strips between piles is more or less like this, based only on deformations, but that's not true. We also measured the vertical pressure in the German tests I showed. Of course, most load goes to the piles, because the piles move least. Yeah, I think I meant that this is the summary. That's so. Oops. These here we measured the deformations with the liquid leveling system, and yeah, the other one we use in experiments. And here we have experience with optic fibers in this same project. I told you these are optic fibers with brags. You see small disturbances in the optic fibers, and you can measure the difference in length between the brags, even in a high velocity. So a passing truck can be measured really nicely, also after years. And these are the systems that we used in the recent ULab experiments. I think I have more pictures about it, but on the left-hand side, we see the XYZ measurements. So they have several optic fibers combined together in one cable. And we installed it just into the sand fill. And then we kept the XYZ. So all the deformations of each point of the optic fiber we can have of the full fill. It's really amazing. But I told you already, it's a lot of work, the data handling. The second one is an epsilon sensor there that measures the strain in the soil. So it's just put in the soil, and you see an optic fiber like this. And from this, they calculate or they can determine the strain in the soil. And the last one, we glued optic fibers on the steel reinforcement in this case. And that gives the strains in the steel reinforcement. This is in the field, same system in the field, X, Y, Z. And here we see it installed in our lab tests. We see the transparent plastic contains the XYZ measurements. So it's relatively flexible and it can follow the scent. And then in between, we see the black-white cables are the strains in the soil. And we installed this at several levels in the sand fill. This is really amazing. And you need a good, the main investment is the data acquisition system, because you really need an expensive device to connect all those fibers to. We used a Luna system, that's most known, and we have a Luna system ourselves. That's a bit old agent and can not do this. This is too much. So we had to hire another one that's able to measure all these optic fibers in this test setup. Very simple. This is basically a bicycle gear cable. The first time we used this in our experiments, we just bought all gear cables of all bicycle shops in Delft. And the idea is you have a stiff steel cable in a tube, and the stiff steel cable is pulled out the tube when you have a tensile strain, and you measure the difference between the two. And we have it nowadays in a more professional way, but it is very basic, and it works. Because it is basically difficult to measure strain in a geosynthetic, because the strains tend to be quite large, so a strain gauge will not measure beyond its own rupture strain, and you cannot attach it well to in many cases. Here we attached, we made a device ourselves to measure in the field the strains. Finish in 2 minutes? Yes, I can. These are optic fibers attached in the field. Yeah, we will. These are all strains measured in different directions in the test setup, and that gives different results. You see that in the strips between the piles we have large strains, and at all other locations we have no or nearly no strains. So measuring deformations, we have seen that measuring deformations can give you the distributed load. That's an important thing to take home. You do not always need to measure load. Now, the result of all this research on the piled embankments was this concentric arches model that is adopted, as Miguel told you already, in a guideline and is in daily use now in several countries. And then these were adopted in this guideline. So far, my presentation. I think we will continue at 11. Maybe you. Yeah?
So maybe a quick question, if someone has. Yeah.
So thank you for your presentation. Actually, I have a question from the very beginning. You told us that aging cannot be modeled in the centrifuge. So I was wondering why. Because you also said centrifuge is a time machine, so it could be like
a centrifuge you can use for all processes where the stress is the driving force, and so maybe tiring when you model something and stress, maybe that can be modeled. But if the chemistry of the material has to change due to aging, it cannot be done in a centrifuge.
But aging can also be a reason of mechanical mechanical movements and like due to creep effects. So that's it's not always chemical. It depends if there's water, for example.
Yeah, that is true, of course. Aging is a difficult word. It can mean a lot.
That's true.
When it's something is chemistry, no, but creep, yes. If you have sufficient long loads on a certain thing that creeps, then it creeps. All material behavior in a centrifuge remains the same. So if it creeps and the load is long enough, then it will creep. But it takes time, of course. But
I don't know if someone has done creep tests in the centrifuge. Is it that can you also take the time as a like?
No, it's not a time machine in this case.
So you need the same time in 1G experiments.
Yeah.
Maybe I need to say something.
Yeah.
It is a time machine because of a scaling. Okay, yes. So for example, if you are trying to simulate a problem related to consolidation, okay, we said yesterday diffusion is scaled by n to the square, right? But the centrifuge is not doing anything magic. The only difference is that the dimension is much smaller.
That's true.
So in reality, instead of having, let's say, 20 meters that need to consolidate, at 1/100, you will have 20 centimeters. So it's purely the size that renders a centrifuge a time machine. So it's not doing
that's a consolidate, but also the permeability scales.
Permeability
scales and the size is n times smaller, and the permeability is n times larger, which results in n squared.
Yes,
for consolidation.
Yes, but the material we're using is the same. So actually permeability is not really scaled. So if you do a clay layer of 20 centimeters in the centrifuge or outside the centrifuge, submitted to the same stress level, it will consolidate in exactly the same time. The only difference will be the gradient. But the gradient, if you put a big enough pressure on top, perhaps doesn't make such a big difference. So it's the size that is rendering the centrifuge a time machine.
Okay. Yes.
So if it is related to chemistry, I don't think that chemistry will be accelerated. So as Suzanne already said.
And creep behavior, you cannot accelerate the creep. The creep occurs in the normal time.
Right, thank you.
Schedule. Yeah.
Wonderful. So then, for the sake of the cookies, we finish this part of the session now. Please feel free to approach Suzanne for more questions. Thanks again. And we will be back in probably at 11:05. So 15 minutes of break. Thank you.
I'm not sure if this is part of this or not.
Yes, this is really part of this.
Okay.